Okay, so the software will come in here when we come to the computer implementation of finite element method. But before we look at finite element method, we shall first look at what we call the direct stiffness method. And then from there, that will lay the background to this method we call finite element method. And then we look at the mathematical formulation, and then the computer implementation. After that, we shall then look at the second part, which is more or less disconnected from the first, coming from the statistics point of view, which we call stochastic random processes. So we shall look at stochastic random processes. We shall characterize them, classify them. And then after that, I will look at estimation theory. So under estimation theory, we look at methods of estimation of parameters. For instance, we look at point estimation and interval estimation, and then we look at the properties of point estimators. For instance, unbiasedness, efficiency, sufficiency, and so on. And then after that, we shall look at methods that we use to estimate parameters. I'll look at specifically two, the method of maximum likelihood, and then also the Bayesian estimator. And then we shall end that part with mean square linear estimators, and so on. So basically, this is the course outline. The first part comes more or less from engineering. The second part comes from statistics and statistics. So the second part is more or less disconnected from the first, but together the three will give will basically lay a basis to this course, advanced engineering mathematics. So most students from, I think, structure mechanics find the first part easier, and there is always some form of complacency. So because they think it is more or less close to what they do, and then people don't usually pay a lot of attention. And at the end of the day, people fail. So assume that you are seeing this for the first time, and then put in all your efforts to try and understand the concepts that are presented. And I think because of the environment that we are using, I will always get good attendance, because usually in physical lectures, a number of students would not appear. But I think with virtual framework, even if you're in a Guru, you could pretend to be working behind your computer, and then you switch on the Zoom and you attend the lecture for at least 1 hour. I think this would be good for you. Okay, so is there any question so far? Okay, so silence means no question, I would suppose. Okay, so now I will move to the direct stiffness method. What is the direct stiffness method? And I'm going to use a different method. Maybe other people use a different method, but I'll use a different method of presentation. So I will use my whiteboard and I write equations as they appear. And then the detailed notes, I will upload them on the Mwere system so that you could look at them. Okay, so I want to look at the direct stiffness method. So what is the direct stiffness method? So I'll stop sharing the screen now and I open another document that involves what I want. Suppose it is this one here. Don't mind about the symbols. Okay, so what is the direct stiffness method? So the direct stiffness method is a matrix method that makes use of member stiffness relations for computing member forces and the member displacements in structures. So it's a method that makes use of member stiffness relations in computing member forces and displacements in structures. Remember, I told you I will start with the direct stiffness method, and then afterwards I move to, from this method, then I'll move to what we call the finite element method. In fact, this method gave rise to what we call the finite element method, and we shall see why. So it originated from the field of aerospace, but I will ignore the history behind this method. I'll move straight to the definition of what we call stiffness. Okay, so what is stiffness? So stiffness, we can define stiffness because the method is direct stiffness. So at least we need to know what we mean by stiffness, and later we shall see why it is called the direct stiffness method. Okay, so what is stiffness? So stiffness, we can define it as force per unit displacement. Force per unit displacement. So if you get force and you divide by displacement, the quantity that you get there is what we call stiffness. Force per unit displacement. And to really understand this method, we are going to look at the behavior of a linear spring, under a loading. If you load a linear spring with some force, how does it behave? Okay, so let us consider a force capital F, denoted with capital F, acting on a spring, and we assume that the spring undergoes a displacement D. So let's assume you have, let me unbold this font so that I emphasize this. Okay, so I want to consider a force F acting on a spring, and I assume that the spring undergoes some displacement D. So this is the scenario I'm looking at here. I have my spring, and so this spring, you load it with some force F, okay, in this direction. So this direction, you load the spring with this force F in this direction, X direction. So the spring will extend and it undergoes through a displacement D, like this one here. So the question now is, if we assume that the spring has stiffness K, then Hooke's law states that the force will be directly proportional to the displacement. Or in other words, if you keep loading the spring, I think this is high school physics. If you keep loading the spring with the, if you have your spring and you load it with some force F, and then you create some kind of a table where you have force on one direction in one side and then displacement D on the other side. So you keep recording these values, force and displacement, force and displacement, and you plot force versus displacement. So the displacement could be on the x-axis and the force on the y-axis. The force values on the y-axis. So when you plot that, then what we observe, or what Hooke's observed, was that the force was proportional to the displacement, and the constant of proportionality is what is referred to as the stiffness of the spring. Okay. I will ask those people with a bad background to mute the microphone so that we don't have the disturbance from there. Okay, so the force, if one plots the values of the force against the displacement, then you get a straight line. through the origin. And if you get find the slope of that line, you find that the slope of the line actually is given by K. And that K is the stiffness of the spring. Or in other words, force divided by displacement gives us the stiffness of the spring. So this is a situation where we have just one linear spring. Now the question then arises, suppose you have more than one spring, what happens? Suppose you have more than one spring, how would you compute the displacement in each of the springs? And if you have not more than one, but you have about 5 or 10 or a million springs, how would you compute the force in each spring and the displacement in each of the springs? Okay, and this is something that we want to look at now. Okay, so we know we shall, of course, the Hooke's law will form a basis of what we want to do, that force is equal to some constant times the displacement. And this will form a basis of what we want to do if we have a system of more than 1, 2, or 3 springs. What will happen? What happens? Okay, so now let's move. Now let's suppose now we have a system that is composed of 2 springs loaded by. So let's now consider a system composed of 2 springs loaded by external forces, as shown below. So I have 2 springs, spring 1 and spring 2. Spring 1 has spring constant K1, and spring 2 has spring constant K2. So we are going to load these 2 springs with the 2 forces. So if there is we are going to load it with some external forces. So let's suppose spring 2 is loaded. There is a certain force acting here given by F3 in the X direction, and then there is a certain force acting here given by F2 but in the X direction, and then there is some force over here which I'm calling F1 X, which is a force F1 acting in the X direction. So we have 3 forces, F1 X, F2 X, and F3 X. These are forces acting in these 3 positions but in the X direction. So K1 and K2 will be the stiffness of our springs. So the problem we have is to analyze the behavior of this system above here. We want to analyze the behavior. Suppose we load this system of 2 springs with the forces shown above. What will be the corresponding displacements? Suppose we load the forces, so the springs with these forces and these stiffnesses, K1 and K2. The question is, what will be the corresponding displacements? So we want to have somehow come up with a relation between force and the displacement Okay, so given force and the spring constant, what will be the displacements? Okay, in case you have a system composed of 2 springs. Are you still with me or not? Let me pause a little bit.
Doctor, we are with you.
Okay. All right. Now,
Doctor, we are with you.
Okay, thank you so much. Now, let's move forward. So the problem is we want to analyze the behavior of this system of springs. And how do we do it? We are going to, we shall start with step number 1 is to discretize. Okay. So in order to analyze the behavior of a system, to analyze the behavior of a larger system, it is always important to analyze the behavior of one part, a smaller part, and then generalize it. So we shall refer to that as discretization. So we shall break up this system of two springs into smaller parts, i.e. elements. Okay, and these elements will be connected to each other through nodes. Okay, so I have 2 springs. I'll break them into elements. So in other words, I'll have 2 elements. The first spring will be my element 1, and the second spring will be my element number 2. And then these elements will be connected by nodes. So these nodes shall be numbered. This will be node number 1. The middle one will be node number 2, and the other one will be node number 3. So what do we know? We know forces acting on these nodes. We know F1x, we know F2x, and we know F3x. What we do not know are the displacements, okay? The displacements in these nodes. We know the forces, we know the spring constants, but we don't know the displacements. So the unknowns are the displacements. We don't know the displacement d1x, we don't know the displacement d2x, and we don't know the displacement d3x. So given F1, F2, F3, K1, K2, our goal is to determine the corresponding displacements, d1x, d2x, and the d3x. The moment we have them, then we know we have already solved the system, and that method shall be called the direct stiffness. Given the stiffness and the forces, one computes the displacements. Okay, so direct because you're given the stiffness. So given the stiffness and the forces, find the displacements. Or given the stiffness and the displacement, find the corresponding forces. Okay, so that's what we want to do. Okay, so break up the larger system into smaller parts. So we call that one discretization. The smaller parts shall be called the elements, and they are connected to each other through what we call nodes. And our goal is to determine the displacements, d1x, d2x, and d3x. So step 2 is to analyze the behavior of a single element. So let's look at a single element or a spring, and then we analyze its behavior. All right, I think I don't have the write-up here, or a good write-up for that here. I think I don't have a good write-up, so I will have to write it myself now. Okay, so step 2 is to analyze the behavior of a single element. So let's do that. Let me now share another window. Okay, now what I'm going to do is I'm going to consider a spring.
I hope you're muted.
Okay, so I'm going to consider a spring with a length L. Okay, the spring will have length L. So the distance from here up to here is going to be L. Okay, so the length of this spring is L. So it has two nodes. So the two nodes, so the spring has two nodes. These nodes, I'll number them 1, 2. And I will assume that we have nodal displacements. The nodal displacement are, so locally the nodal displacements will be, I'll assume that the displacement here, suppose this is node 1 and this is node number 2. So the displacement there shall be denoted with the d1x, but I'll put a hat to denote that it is a local displacement. And then the displacement in the second node shall be called d2x, but with a hat on it. And the nodal forces, lastly, we need the nodal forces. Okay. Nodal forces. So the nodal forces shall be denoted by F1x. I'll put a hat to denote that it's a local force, and F2x to denote that again it's a local force acting here. So I'll assume that the spring has a constant K. So the spring constant is K. Okay, now what happens is the spring is going to be loaded with a force, okay? And then it will undergo some kind of, it will undergo some displacement, okay? So let's assume this spring is loaded, when loaded with the force, forces F1x and F2x. So we shall have some force here, F1x hat and the F2 x hat. So when you load it with this force, that it force possibly F2 is bigger than F1, that it goes through displacement in this direction. Okay, so let's look at that situation. So suppose we have this spring of ours. This is the original one. And then after loading, okay, when you load it with these forces, then it will extend. I don't know how best to draw it. Let me try. So when I load it with the forces, this spring will undergo some kind of displacement. Maybe like that. Okay, so now we have, this was the original length. So the original length is from, so this is the original length, let's call it capital L. Now the new, so when you load it with some force, let's suppose that it goes through some displacement, and then, so we shall look at, let me do some, sorry. Let me do some line here, and then some other line here. So this will be the displacement I will call D2x, okay? D2x. So this displacement here will be, this distance here will be D2x. But I'm going to give it a hat, okay? So the original length, so the original length is L, is equal to capital L, and then the new length would be equal to what? So it will be equal to, so if you take, so if this, so this spring goes through some displacement, I'm calling it D1x. Okay, D1x hat, and I think let me redraw this so that it is very clear. I think it's not clear as it is drawn. Let me try to draw this very clearly. So we have our spring. Like this. So originally, the spring has length L. Okay, I don't know how much time I have, 5 minutes, okay. I'm using a free license which breaks off after 40 minutes. So after, when it breaks off, we shall have like a 5 minutes break, and then you can log in again using the same link. Okay, so in case it breaks off, know that we have a 5 minutes break, then you log in again with the same link. Okay, so this is the original length, and then when this spring undergoes, you apply this force F1 and F2x, it will go through some displacements D1x and D2x. So let's suppose now the new location of the spring is here. So let's suppose the new location of the spring is like this. Let's suppose it's now like this. Okay. Yeah. Okay, so let's suppose this is now our spring after loading the forces. Okay. Now, so this distance from the distance from here up to here, I want to call it d2x. I want to call that, so d1x. I want to call that distance from here up to here. Let's call that d1x, d1x hat. And then the distance between this one and that point, that distance, let's call that d2 x hat. Okay, now what's the original length? So the original length is L. What's the new length? So the new length would be L. Okay, so the new length would be L. If you add on d2x minus d1x will be my new length. So the new length will be L. Okay, so the new length will be L minus d1x hat plus d2x hat. Or in other words, the extension, which will be d2x hat minus d1x hat plus L, will be my new length. Okay, so the new length will be L minus d1x hat plus d2x hat. So the extension then would be the new length minus the original length. So the extension basically would be so extension would be d2x hat minus d1x hat. So the extension would be d2, d2x hat. I'm using a mouse to write, so my writing may be bad because I'm using a mouse. d2x hat minus d1x hat. That will be the extension. So we shall use these coordinates, very important. We shall use x hat to denote the local coordinate, and we shall use x to denote the global coordinate. And I'll explain this a little bit as we go along. Okay, so I have less than a minute, so I will start from here. Let's have a short 5 minutes break, and then we start from here. 5 minutes break, and then you log in again, and then we start from here. Okay. 5 minutes break, please.